In this video, I want to work through two problems that ask us to differentiate inverse trig functions. So our first problem asks us to differentiate cos inverse of 2x plus 1 and state the domain. So I want to have a look at this domain part first. We know that if we had the function cos inverse of x, then the domain restriction we would put on that is that x is between minus 1 and 1. So that means that if we have cos inverse of 2x plus 1, then that whole 2x plus 1 has to be between minus 1 and 1. So our domain would be that minus 1 is less than or equal to 2x plus 1, which is less than or equal to 1. If we subtract 1 from both sides, we'll have minus 2 is less than or equal to 2x is less than or equal to 0, and then divide both sides by 2. So our domain is going to be that x has to be between minus 1 and 0. So we just need to double check that again at the end, but we'll leave it there for now and we'll come back to it. All right, so we're starting with the function y equals cos inverse of 2x plus 1. So to differentiate this, we're going to have to use the chain rule. So we're going to differentiate the outside and leave the inside alone. So that's differentiating cos inverse, and instead of x, we've got this whole 2x plus 1. And then we're going to multiply by the derivative of that inside. So let's have a look. So we're going to have y dash is equal to, we know that cos inverse differentiates to minus 1 over the square root of 1 minus, normally it's x squared, but instead of x, we've got this whole 2x minus 1. So we're going to have that 2x minus 1 squared. And then we're going to times by the derivative of the inside function, which would just be a 2. So now we're going to have minus 2 over the square root of 1 minus, and I'm going to leave this in brackets while I expand this out. So I'm going to end up with 4, that did not look like a 4. I'm going to end up with 4x squared minus 4x plus 1. And if I simplify that bottom a little bit, expanding out that bracket, you can have the square root of 1 minus 4x squared minus 4x minus 1. So that minus 1 and the 1 at the start cancel out. So I'm going to have minus 2 over the square root of minus 4x squared minus 4x. And I'm just going to factorize what's in the denominator under the square root sign there. So I'm going to have minus 2 over the square root of minus 4x outside of x plus 1. Now there is more I could do to simplify it if I wanted to. I could square root that 4 and then cancel out the 2's. You don't necessarily have to. So that's fine, that is my derivative, but I just need to double check my domain. So what I had up here was that it's between, minus 1 is less than or equal to x, which is less than or equal to 0. But if you have a look at this function that we have, x can't actually be equal to minus 1 or 0, because if it was 0 here, that would make the denominator 0. And if it was minus 1, it would make this bit 0, and we know we can't have a denominator of 0. So this actually isn't our domain. What our domain is minus 1 is less than x is less than 0. Our second example asks us to differentiate the function y equals sine inverse of cos x, and hence sketch the graph of y between minus pi and pi. So again, we're going to have to use the chain rule. So if we differentiate this function, we're going to have y dash is equal to, if we differentiate the outside, leaving the inside alone, so differentiating sine inverse, we're going to have 1 over the square root of 1 minus, normally it's x squared, but in this case our x is cos x, so we're going to have cos squared x. And then we're going to multiply it by the derivative of the inside, so the derivative of cos x is minus sine x. All right, so if we simplify that, we're going to have that minus sine x as our numerator. And in the denominator, we know that 1 minus cos squared is actually just sine squared x. Now it's very, very tempting here to go, okay, well, if we're taking the square root of sine squared, then we're just going to end up with minus sine x over sine x. But we just need to be careful that we're being really precise. So if we have something squared and then we take the square root of it, this will always give us, so the square root of sine squared will always give us something positive or 0. Okay, so it's always going to be positive. But if we just have sine x, that could be positive or negative depending on what x value we put in there. So these two things aren't exactly equal. So to be really precise, what we actually need here are absolute value signs around that denominator. Okay, so that's going to make a difference. So this is our, I'm going to write those in blue instead because they're annoying me. This is our derivative, but the next thing we're asked to do is to sketch it. So I want to do two things. I want to find the values at the bounds, which we're going to do in a minute, but I also want to consider what's going to happen with the gradient of this function. So this derivative is telling us about the gradient. If we have a look at that, when x is between 0 and pi, so when x is a positive value, then we know that sine x is going to be equivalent to, it's going to be equal to, the absolute value of sine x. Because if if x is between 0 and pi, sine x is going to spit out a positive value. So that means that here we would have minus something over itself. So we would just end up with, so therefore the gradient is equal to minus 1. The opposite happens when we look between minus pi and 0. So when we do that, sine x isn't going to be equal to the absolute value of sine x because sine x is going to give us a negative value. So we'd actually have to put another negative in front so that when we take sine x and get a negative number, that negative then turns it positive again, so it does equal to the absolute value. So that means that when we're between minus pi and 0, this whole function here is just going to give us a gradient of positive 1. All right, so that means that our bounds, we are looking at minus pi and pi, but the gradient also changes at 0. So I want to know what's happening at 0 as well. So let's just have a look. When x is minus pi, I want to know when x is 0, and I want to know when x, that's a pi, I want to know when x is equal to pi. I want to know the y values at all of those points. So then I have 3 points and I don't know the gradients between them. So I'm going to substitute these values into the original function, and I'm going to end up with minus pi on 2, and minus pi on 2. So then I can draw my graph. Now I can't use a ruler on this thing, but I expect you guys to. Okay, so down here we have minus pi. Up here we have pi. Down here we're going to have minus pi on 2. Yep. And up here we've got pi on 2. So we know that at minus pi on 2 we're down here. At minus pi we're down at minus pi on 2. At 0 we're up at pi on 2, and at pi we're back down here again. We also know that the gradient between minus pi and pi is 1, which makes sense looking at the graph. So we're going to have a straight line going up here. And we know that between 0 and pi our gradient is minus 1. So that's going back down this way. Oh gosh, wrong button. All right, so you might want to use graphing software to confirm what that actually looks like when it's drawn very neatly. But that's the general idea of our graph. So that's 2 examples looking at differentiating inverse trig functions.